Okay, so welcome everybody to this session about routing and mobility. The first talk is about, it's titled Insertion Sequence Variables for Hybrid Routing Scheduling Problem. The paper is by Charles Thomas, Roger Kameugne, I don't know about the correct pronunciation, sorry, and Pierre Schaus. The presenter is Charles Thomas.
Hello everyone, my name is Charles Thomas and welcome to this presentation. So today I will present our latest work on sequence variables. So what exactly is a sequence variable? It is a CP variable that will represent a set of elements or events to order. So we could use that, for example, here to model the itinerary of a vehicle that needs to visit several people. And so our domain will be the set of all possible combinations for this visit. Once the variable is bound, it will be linked to a single combination that will be the visit of our vehicle. So sequence variables are already implemented in CP Optimizer and Google Earth tools. However, these variables are not detailed yet in the publication and use specific interval variables that represent activities. The implementation is based on a head-tail graph domain. So the idea is that two things will be maintained during the search that represent the head and the tail of the sequence that will be built incrementally by adding non-sequence activities to either the head or the tail of the sequence. Our contribution is a new implementation for a sequence variable that is based on insertions. So it allows to add elements at any place in the sequence during the search. The sequence contains integer elements, so it is a bit more generic, and it extends the set variable. So in order to implement the set domain, we use sparse sets. So the set domain is basically a partition of the set of all elements. Initially, all elements are possible, and during the search, they will be moved to either the required subset or the excluded subset, meaning that the element is either present in our sequence or excluded, so it will not be part of the sequence. The set domain is extended with an internal sequence. So the internal sequence is implemented with an array of reversible integers. For each element of the sequence, we will have an associated reversible integer that will indicate the next element in the sequence. So a bit like a successor model for a routing problem. So in order to insert an element to an empty sequence, we have a specific element bottom that represents the start and the end of the sequence. And so we can insert an element after bottom. So we will simply modify the value of the reversible integer to reflect the new state of the sequence. Elements can then be inserted at different positions. So for example, here we could insert F between bottom and B, so meaning that we insert F at the beginning of the sequence, and we will simply change the state of our reversible integer array to represent that. Additionally, our variable maintains a set of possible insertions for each element. So each element of the sequence is associated to a reversible set that contains all the possible predecessors after which this element could be inserted in the sequence. So for example, with the state of the sequence, F and B are both already part of the sequence, so they cannot be inserted anymore. For the other elements, F and B are both present in their possible predecessor, as well as bottom, and as well as the elements not yet sequenced. So if an element is excluded, then its set of possible predecessor is emptied, and it is also removed from the other element's predecessors, as it is not a valid predecessor anymore. The constraint can also use this structure to remove some insertion. For example, here, if we have a precedence between F and E, that means that we cannot insert E before F in the sequence. So bottom will be removed from the possible predecessors of E. Similarly, if B is said to be the last element of the sequence, then it will be removed from the possible predecessors of C and E, as it is not a valid predecessor anymore. So graphically, we have this state. We developed several constraints for our sequence variable. So I will in the paper I detailed two of them. So the transition time constraint, which links the sequence with time windows. So the idea being that the sequence represents a series of events, and each event is associated with a time window that is characterized by a start and a duration. So both of these are CP integer variable. And furthermore, we have a transition matrix that will indicate the time that it takes to transition from one element or one event to another. So the filtering for this constraint is done in several steps. So the first of them is to ensure that given the current state of the sequence, the time windows are respected. So we will update the time windows based on the transition time and their current state. So for example, here we have to update the bound of the time window for P, as we need to take into account our transition time between A and B. And we will do that linearly by following the sequence in one or in the order. And afterwards, we will follow the sequence in the reverse order to do the same operation in order to update the other extremities of the time windows. Once the time windows are updated, we update the possible insertions. So we will check that for each possible insertion, we can indeed perform this insertion and still be valid regarding to our time windows. If at some point we see that a possible insertion will lead to a violation of the constraint, we remove this insertion. So for example, here, we will remove B from the possible predecessor for C. The third step is to check that all the required elements in the sequence can still be inserted in the sequence. So in order to do that, we will use a depth first search. We will start from the start of the sequence, so bottom, and we will check whether or not we can insert elements that are required. Once a required element can successfully be inserted, we keep track of this insertion. So we remove it from the required elements that we still need to check the insertion for, and we check the insertion of the next element. If at some point we have excluded all our possible insertion without being able to insert elements, we move to the next element in the current sequence and we repeat this process. So once we have been able to successfully insert each element, we know that there exists a feasible path for these elements. This algorithm is also used for filtering purpose. So to do that, we will add so for each possible element, we will add the possible element to the set of required elements and rerun to algorithm to check that the combination of the required element and this possible element is still possible. If it's not the case, we know that the possible element is not insertable in the sequence and thus can be excluded. So this algorithm has an exponential time, so it's quite expensive. So to deal with that, we use a cache, and we limit the depth of the depth first search by having an additional parameter. The other constraint is the cumulative constraint, which is used in the case of the sequence where the sequence represent loading or unloading events. So the constraint ensures that given the state of the sequence, all the activities can be performed without overloading the capacity. It will mainly remove insertion if we detect that at some point we will violate the capacity by using this insertion. So we tested our implementation in a model for the patient transportation problem, which is a variation of the diarrheal program. So we compared our model with an implementation using CP optimizer, which is this blue line here. Our implementation had two different heuristics that were tested. So these are both the continuous lines. So the red line is a simple first phase heuristic, which is generic, and the green line is a problem-specific heuristic. And finally, we compared also our implementation with a dedicated scheduling model for this problem. So the graphs indicate the anytime relative distance. So this is the ratio between the current solution and the optimum solution, and it is averaged over 60 instances. We had two experiments, one using a large neighborhood search, where we use the large neighborhood search of CP optimizer, where we can see that our variable has performance slightly better than CP optimizer and quite better than the dedicated scheduling model. We also compared the different approach in a depth first search setting, so for a complete search, without using large neighborhood search. And we can see that CP optimizer is really not performing well in this setting. So that could indicate that the specific search of CP optimizer plays a big role in order to be to have a successful to be efficient. So we can see that the performance of the first phase heuristic, so the generic heuristic, are quite comparable to the scheduling approach, and the problem-specific heuristics yields better results. So in conclusion, we presented a new sequence variable with an implementation. So this implementation is generic. It allows precise pruning on possible insertion, and we also implemented several constraints for this implementation of the sequence variable. So the implementation is available on the OSCAR solver. In the future work, we would like to add new propagation algorithms in order to improve the performance of our constraint. And it will certainly be possible to use this variable for other programs and maybe develop new constraints dedicated to this variable. Thanks for your attention.
So thanks for the presentation. It was very nice and very clear. So I have just a quick question. So have you considered applications about scheduling, for example, production scheduling problems with the setup times?
Yes. Can you hear me?
Yep.
Okay.
You have very, very short time.
So we considered several applications, and indeed it could be used in production planning. For example, the setup time could be represented either by additional activity to add to the sequence, or by transition times. So that's a possibility. And in fact, I believe that this variable could be used in many problems, including scheduling and routing problems.
Okay, many thanks. So next talk is about transfer expanded graphs for on-demand multimodal transit systems, and the paper is by Kevin Dalmeijer and Pascal van Hentenryck, and the speaker is I guess it's probably Kevin.
That's right. Hello everybody, thank you for attending this talk. My name is Kevin, and I'll be presenting joint work with Professor Pascal van Hentenryck called Transfer Expanded Graphs for On-Demand Multimodal Transit Systems. I have the following planned for today. I'll start with an introduction and a motivation. So which problem and why do we want to solve it? Then we'll look at a Bennis decomposition approach. We'll look at transfer expanded graphs. I'll explain what they are and why we actually need them. And we'll discuss computational results. So to start, we'll start with the motivation. This work that I'm presenting today is part of the work of the Socially Aware Mobility Lab, which is the lab led by Pascal van Hentenryck at Georgia Tech. And the goal of the lab is fostering an equitable and accessible transit system in Atlanta. And there's a lot of reasons why you want to care about your mobility system. Mobility systems improve access to jobs, to healthcare, to education, to healthy food. So really, an equitable and accessible transit system is something that's really important. On the other hand, if we look at how the current system is used, we see that in Atlanta only 2% of commuters make use of public transit, which is low. If we compare this to some other US cities, like Boston, for example, we're talking about 15%. So 2% is low. And the main reason that this is so low is due to poor convenience and poor availability. Well, to try to improve this situation, we've been exploring on-demand multimodal transit systems. And these systems look like the picture on the right. So you have some high-frequency connections. So on the right, these are rail in red and buses in blue. But everything else is served with on-demand shuttles, ride-sharing shuttles, like Uber and Lyft. And how it works for people is you are somewhere at the origin, you type in your destination, and the system provides you a route to get there. So in this case, a shuttle will come to pick me up, drop me off at the train station. I'll take a train, then I take a bus, and then another shuttle is already waiting for me to bring me to the final destination. And a nice way about these sort of systems is that you get the best of both worlds. On the high demand corridors, you have these high frequency, high capacity vehicles, and everywhere else you have shuttles, which are on demand and only serve when you need them, which means you can give better access and you can actually serve regions where it doesn't make sense to run an empty bus most of the time. Well, this problem has been considered before by Michele et al., and they call it the ODMTS design problem, which is the problem to decide on the high-frequency connections. And the objective is mainly to minimize the cost of the systems, of the design, but also the cost or the objective that the passengers experience. So that's our starting point. And then we go to the contributions that I want to talk about in this talk, which first of all, we generalize the ODMTS design problem to add 3 things that are really important in practice and which had not been considered before. First, we consider multiple frequencies. So instead of just always having a bus that arrives every 10 minutes, you can, for example, also choose a bus that arrives every 5 minutes, etc. We include multiple modes in the model at once. So not just trains or buses, but we can do trains, buses, and any other mode that you want to add. Third, we impose a limit on the number of transfers. Because nobody wants to go in a shuttle, in a bus, in a train, in another train, in a bus, and then finally arrive somewhere. So we have a limit on the number of transfers you can do. Well, the second contribution is that we actually present a Bennis decomposition method for this generalized problem. This extension approach by Michele et al., and the extension is pretty straightforward for the multiple frequencies and multiple modes. The main difficulty is dealing with this transfer limit in a computationally efficient way. And the solution for that will be transfer expanded graphs, but we'll talk about that in a couple of slides. Let's first look at the standard Bennis decomposition approach. Starting with the master problem. So in the Bennis decomposition approach, the master problem consists, or is the question, to decide on the high frequency connections, so the buses and rail. I've given the formulation. I won't discuss all the notation because we don't have time. But the important things I'll point out, of course. So first we have the decision variables, which decide which arcs, and an arc is defined by from, a to, a mode, and a frequency, are selected. So for example, in this case, I have a bus network of 3 arcs, which means I have 3 variables, which are 1, the first of which is Z12 bus 3 per hour, which means I have a bus from 1 to 2, and there's 3 buses every hour. Then the objective is to minimize the cost of this system, so the high frequency connections, plus the passenger objectives, which are modeled by the function phi. Well, this function is calculated in a subproblem, so I'll worry about that later. Then we have frequency balance. So if you have 3 incoming buses per hour, you also want 3 buses to leave. And we have the restriction that you can only select one possible frequency for every arc. So that's the master problem. Determine the high frequency connections. Then we have the subproblem. And the subproblem amounts to a shortest path problem for every passenger to find the cheapest way to go through this network. First, I want to point out, so we have these flow variables to model how passengers flow through the network. And I want to point out that these can be continuous. This is because the shortest path problem has the integrality property. So we have total unimodularity. And we don't actually need to enforce integrality, so 0 or 1. We can have continuous variables. And these variables would look like this. So I have a passenger going from origin to destination, and the flow is defined by these y variables. The objective is to minimize the passenger objective, which is a sum of some sort of objective over the arcs. I can only use high frequency connections that are actually chosen by the master problem. So in this case, I use buses, so these buses have to be available. And then we have the classical flow balance for shortest path. So this is the subproblem, and I wrote down the subproblem for all the passengers at the same time, but it's important to notice that this is decomposable. For every passenger, you can just solve a separate shortest path problem and solve the subproblem in that way. Okay, let's go to transfer expanded graphs. So say you want to enforce this transfer limit constraint. Well, the naive approach, which was the first thing that we tried, is the following. You'll just add an additional constraint. This one. This constraint simply says that the number of the total flow is less than k, which means that the total number of arcs you can use is at most k, or k minus 1 transfers, alternatively. However, this has some negative consequences that we would have to deal with. First of all, these variables can no longer be relaxed. They can no longer be continuous because the shortest path problem with side constraints is no longer totally unimodular. Well, that also means that this value function phi z is now suddenly not convex anymore. Even worse, because this function is not convex, Bender's cuts are no longer sufficient to solve the problem. There are ways to deal with this. For example, you can work with combinatorial Bender's cuts. But from a computational standpoint, this means that things will be much more difficult to work with. Our solution to deal with this is transfer expanded graphs. And transfer expanded graphs are layered graphs to implicitly enforce the transfer limit. So we expand all the nodes for the different transfers, and that way we try to get rid of this explicit constraint. So I'll demonstrate this with an example for case 3, which means at most 2 transfers. On the left, we have the original graph for one passenger, so an origin and destination. I made the gray lines thinner. This will be more clear in the next picture. And the important thing to note here is that we have to enforce the constraint that the total number of edges is at most 3, because otherwise we could find a longer path. On the right, we construct this transfer expanded graph, where we take the original nodes, except the origin and destination. We duplicate them k minus 1 times in different layers. And all the arcs between these nodes, we will keep them, but they will always go a layer down. So for example, this first arc on the left will be the new arc on the right, between the same nodes, but 1 layer down. Same for the other 2 arcs. Then we add arcs going out of the origin, and we add all the arcs from all the different nodes to the destination. And what we see now is that on the right, every path that you can make has at most 3 arcs. for the simple reason that every arc that you take, you go down one layer. And because the number of layers is limited, you can do this. So we no longer need a separate constraint. We can simply again solve a shortest path problem, and everything works out nicely again. Well, the reason that this makes sense to do it like this is because K is typically small. So now some computational results. So we did a case study for Atlanta. Details are in the paper, but basically we have two different frequencies for the buses. We have shuttles, buses, trains, and we do at most 2 transfers. And we use real transit data, which is provided by MARTA, which is the local public transit provider. We're talking about 7,000 passengers, and we have a graph with about 5,000 different locations. Well, what we observed here after solving it, and the solution you can see on the right, if we use transfer expanded graphs, as explained, we can solve this problem in about 2 minutes. If we take the naive approach, I have no idea. I never let it finish. It took way too long. So then we tried the naive approach where we relaxed the subproblem. So we relaxed the integrality constraints, even though technically you cannot. And then still, it takes an extremely long time to solve it. And the reason we think that using transfer expanded graphs is so efficient is because you really only explore paths that are short. In this case, that only have 2 transfers. Because even in the relaxed naive approach, you can fractionally explore paths that are way longer. And we think that this explains the large difference in solution times. So to conclude, I presented a generalized ODMTS design problem with 3 additional additions that are very useful in practice. So multiple frequencies, multiple modes, a limit on the number of transfers. And we introduced transfer expanded graphs to actually enforce this transfer limit implicitly. And the computational results on real data have shown that transfer expanded graphs really improve computational performance. So that's it. I'll leave the references on screen, and I also invite you to visit our website of the Socially Aware Mobility Lab. Thank you for your attention, and I'm here for questions.
So thanks again, a very nice presentation, and the idea of using expanded graph in this case was very clever, brilliant. And there is a question by Chris Beck about whether you can use time-dependent frequency for accommodate the fact that maybe during the day you have more buses than during the night.
Yes, thank you for the question. So how we deal with this at this point is that we just solve different problems for during the peaks of the day and like the night and the less busy times, so that we have an actual different design there. But I think we could do time-dependent frequencies because basically you would just have an additional arc. For every passenger, we know what time they leave, so we know we can pick in advance which of the 2 connections corresponding to like the period of the day they use. So there might be some problems at like people who are at the borders of these times, but in the most time, I think we should be able to handle it. Okay,
there is a second question about vehicle capacities. How you enforce them in particular in the sub-problem?
Yes, well, at this point, to be honest, we have the luxury that nobody's using public transit and most of the buses are empty anyways. So we don't have any problems with capacity. So that's the answer for now. So including capacity definitely would make things more complicated, mainly because then you get an interdependency between the sub-problems, so you can't solve them independently anymore. We did think about this, and we might be able to do something with a Lagrangian decomposition there to deal with capacity. In terms of shuttle capacity, we're working on that as well. Here we use an approximation, but if you really want to model shuttle capacity, you could also do it with graphs like these, where instead of duplicating them for time periods, you would duplicate them for the capacity or the number of people in the shuttle, for example. But for buses, the capacity would be too large to do this efficiently. Okay, many thanks. I see there's a small follow-up. Yes, in the Netherlands, this would be an issue. But we'll tackle that later. Let's start with Atlanta first. Thank you.
Okay. So I think you can move to the next presentation. It's about Bilevel optimization for on-demand multimodal transit systems. So again, similar topic. It's by Beste. I'm sorry, I cannot pronounce your last name, and Pascal van Hentenryck. I think Beste is going the presenter.
Yes. In this talk, we will be discussing bilevel optimization for on-demand multimodal transit systems. So public transit design is an important problem in mobility involving various concerns, including first and last mile problem. And to address this problem along with the other aspects of the public transit design, on-demand multimodal transit system provides a key approach to address these issues by providing a flexible system by combining on-demand shuttles with high-frequency bus lines. So in particular, hubs are located at high-density corridors, and afterwards, on-demand shuttles are used as feeders to the bus system through hubs. Then it becomes critical to design the public transit network systems by achieving higher accessibility and convenience for the users through incorporating their behavior into the decision-making process and capturing the resulting latent demand in transit system, while considering its cost to the system as well. So, we would like to answer how we can integrate these user choices and latent demand during on-demand multimodal transit network design while minimizing cost for the transit system and also obtaining the most cost-efficient and convenient route for each user. To formulate this problem, we present a bilevel optimization approach with two players, the transit agency as our leader and riders as the followers. So transit agency determines the transit network design while minimizing the cost of opening legs between hubs and cost of all trips adopting the system, while maximizing convenience of all routes and considering connectivity between the hubs. On the other hand, the followers, the riders, obtain the most cost-efficient and convenient route between their origins and destinations of their trips, given the transit network design. So here we consider the case where transit agency and riders subsidize the cost of the trips equally, so which is why riders determine whether they will adopt the system or not by examining the cost and convenience aspects of the trips. And user behavior can be learned through multinomial logic models or machine learning models. So if we formulate the problem in here, we can observe that the problem 1 corresponds to the leader problem, and the second problem corresponds to the follower problem. So the leader problem determines the transit network design with its decision variable z, the binary variable, and delta r represents the choice function, which depends on the cost and convenience of trip r, which is obtained by the follower problem. So if we examine the follower problem, we can observe that it's in fact solving a shortest path problem from the origin to destination of the trip using the arc weights considered in the objective. And in here, we have two sets of decision variables, x and y, corresponding to the bus and shuttle legs used in that trip. So our next question becomes how we can solve this bilevel optimization problem. To do that, we propose a decomposition algorithm. So we start by first solving the master problem, which is in fact a relaxed version of the leader problem, by omitting user choices. And we obtain the solution corresponding to our transit network design, the user choice, and the DR value. This gives us a lower bound to the true problem. Then we solve the sub-problems of each trip, where each sub-problem is the shortest path problem, and we obtain this value under the given network design z-bar. And we add optimality cuts to the master problem for each trip, which is in fact the Bender's cuts, Bender's optimality cuts. Afterwards, for all trips with choice, we check whether this z-bar and delta r value are consistent with the shortest path value that we obtained. And if there is any inconsistency, then we need to add cuts to the master problem to ensure this relationship between network design and user choices. And in the following slides, I will be going over further about this consistency issue. And then we can obtain an upper bound by constructing a feasible solution, and we then go back to our first step and continue to the iterations until lower and upper bounds converge. Here we note that algorithm converts in finitely many iterations by considering the binary nature of the transit network design and user choices, along with the Bender's decomposition algorithm cuts that we add. So to understand this consistency, let us first formally define what we mean by that. So given this decision variable z, given this solution value z bar and delta bar, once we evaluate the shortest path, like once we find the shortest path value and evaluate it under the choice function, it gives us the choice value. And if this value is equal to the value that we obtain in the solution, then we can say that this is consistent. These are consistent. So we can have two possible cases where in case 1 the solution values are inconsistent and the case 2 is consistent. So if we are in case 2, meaning that these values are consistent, then we do not need to add any cuts. However, for case 1, it means that we need to add cuts for each consistency case, where the first case, like case 1a, represents the case that the master problems gives a solution where the choice is 1. However, the choice function returns the value 0. So in this case, we need to add a cut to relate this z bar variable with this delta r variable in such a way that if z is equal to z bar, then in that case our delta r value should be 0. And we need to also add a similar cut for the case 1b. So more specifically, we propose the following two cuts, where the first cut removes the case 1a and the second cut removes case 1b using the no-good cuts. Then we were thinking about whether we can obtain stronger cuts based on the choice function's properties. And to do that, we consider monotonicity property by defining anti-monotone mode choice functions. So a choice function is anti-monotone if it satisfies the following property in here. And then we propose the following. So if we have a transit network design Z1 with as less legs as with less legs than the transit network design of Z2, then in that case the shortest path that we obtain its value should be greater than or equal to the other one's value, as Z1 has less legs in its design. So, by combining this definition with this proposition, under an anti-monotone choice function, if Z bar is less than or equal to Z2, then we have the following property. So, when the choice function is anti-monotone, then stronger cuts can be derived, as we will observe that although we have different Z solutions, the shortest path value will change in such a way that the user choice will remain the same. So which is why we can obtain stronger cuts for these two cases, for case 1a and case 1b as follows. Then let us consider the choice function in here, where we compare this dr, which is the cost and convenience of the trip suggested by the ODMTC, with the dr car, which is the current mode of travel we assume, as with the personal vehicles of the riders. So in here, if this value is alpha r times the current value, less than the current value, then the user will adapt the system. Otherwise, the user will not adapt the system and continue to use her personal vehicle. And then we propose that this choice function is anti-monotone. So for this choice function, we can use the stronger cuts that we proved in here. So now let's move on to our case study, where we consider a dataset from Ann Arbor, Michigan with 10 hubs located at high-density corridors. Then we examined like 1,500 trips from a dataset from 6 p.m. to 10 p.m. and we conducted pre-processing step to ensure triangle inequality with respect to cost and convenience, which are the weights of the sub-problems, to satisfy some of the assumptions that we have in our propositions. Then we considered a certain set of riders as existing riders and remainders as the riders with switching choices, and we propose an income-based classification for representing rider preferences. So in particular, as income level for rider increases, then she becomes more sensitive to the quality of the system. So for the high income riders, for instance, this alpha R value is set to a smaller one, But however, for the middle income, it's a bit higher one. And for low income, for instance, we assume that they are less sensitive. So which is why we consider all of the users as existing. However, for the other two classes, we consider a certain set of them as the riders with choice, with these parameters. We further consider a distance threshold for the on-demand shuttles as 2 miles. So here's an illustration of an ODM-TC design with 10 hubs where red, gray and green points correspond to the low, medium and high income riders bus stops respectively. So we can observe that all hubs are connected in this design. And if we examine the cost, convenience and the adoption rates, so in the first table we can observe that the adoption rate is really high as most of the users adopt the system, and we can see that the longest average route time belongs to the low income class, but it's also cost time is the least compared to the other one, despite of its long route time, and this is due to the fact that the riders here benefit more from the bus legs and less from the on-demand shuttles, and the middle and high-income class riders benefit more from on-demand shuttles because of the convenience aspects in their choice functions, resulting in more expensive routes. And when shuttle threshold increases to 5 miles, trust network design changes significantly with less hubs utilized and less bus legs open. Furthermore, I want to mention that with more ridership considered as latent demand with choices, the ODM-TC opens more legs and further reduces congestions and keeps a high level of convenience for the riders adopting the system, providing a more robust solution under new formulation. And please check out our paper for further details of our case study. So in conclusion, we presented a bilevel optimization approach for modeling the ODM-TC design problem by integrating rider preferences and considering latent demand. We proposed a decomposition algorithm for the efficient solution of the bilevel problem and developed cut generation procedures based on the specific properties of the choice function to satisfy the relationship between the network design and the rider choices. And at the end, we demonstrate the potential of this approach on a case study over Ann Arbor, Michigan, as ignoring latent demand can lead to significant cost increases for transit agencies. Thank you very much for your time, and please stay tuned for the extended version of this paper with further theoretical results and practical insights.
So, thanks for the presentation. I appreciated a lot also the theoretical contributions. So I have a possibly strange question, actually, which is more on the practical side. So estimating a latent capacity can be quite tricky, finicky thing. And if you have a method that is very sensitive to errors in that estimation, that may lead to mistakes. Have you tried to assess that, for example, by running the algorithm different times and sampling different pools of latent customers?
So I think that this is a great point that we need to investigate further. So currently we made some certain assumptions regarding our existing riders and the riders with latent demand, like the riders with choice, based on income. But this might not be only based on income, and we might need to consider more aspects while we are making this. So I think like this is a point that we need to investigate further. Okay, thank you. So if there are, and there is another question by Kay Hopman. And then another one by Chris Beck. The one is about whether it is possible to formulate the problem using the KKT conditions. Yes, so one way can be to in fact obtain a single stage formulation by using these KKT conditions and like solving the single stage problem. But since it will involve it will require addition of many variables and constraints, like we did not do such a thing and try to do for the composition, right? And also for the LP part, our sub problems, like the ones that are finding the shortest path, are totally unimodular. Like we can solve them as LP because of the fact that like our transit network design is given. So if it's also a decision variable, then in that case we might not be able to benefit from that property. Okay, there is a question by Chris Beck about the fairness of the solution, meaning that mid-income people in particular seem to get the best deal in terms of convenience and price. Yes, so in fact, in here, like in terms of the fairness, so like since we have that switching mode choice functions, depending on that like income classes, so it kinds of, in terms of the trip duration, it bit favors the trips which are from high income classes because we want, because like, so like if they are not favored currently in the system, then they will not be choosing the system. So this is in fact kind of a disadvantage for the users from the low income class. So which is why like we wanted to have some, like in our extended paper, we are trying to address this problem, but for riders from low income class, how we can limit their travel times, or how we can make some further kind of analysis to make sure that we ensure the fairness for each income class.
Okay, thank you. I think we can move to the last presentation in this session. Then there will be some time for question and answers. So the last talk is a short one. It's titled "The Large Neighborhood Search for Distributing Service Points in Mobility Application with Capacities and Limited Resources." It's by Thomas Jatschka, Tobias Rodemann, and Günther Raidl.
Hello, today I want to present to you a large neighborhood search for distributing service points in mobility applications with capacities and limited resources. As the title says, we are dealing with the problem of distributing service points for mobility applications, and our problem formulation specifically considers capacities and resources of service points. We present a large neighborhood search based on mixed integer linear programming for solving such a problem. In general, our problem formulation can be applied to a wide range of mobility applications. However, in this presentation, we will only focus on distributing battery swapping stations for electric scooters. So a battery swapping station contains batteries for electric scooters, and the idea is that customers can travel to these battery swapping stations and exchange the depleted batteries of their vehicles with fully charged ones. And since they travel with electric scooters, exchanging the batteries only takes a few moments. And after the exchange, the batteries are recharged at the stations, and once they are fully charged, they can be provided to customers again. So here we have a short problem description of our battery swapping station location problem. The problem is defined for a whole day, which is partitioned into a set of time intervals. We have a street network on which customers travel, and on some locations in this network we are allowed to place battery swapping stations. And of course, building a battery swapping station and adding charging slots to it is associated with costs. And each station only can have a specified maximum number of battery charging slots. Customer trips are given as origin destination pairs, and for each trip we know the expected number of customers that want to exchange batteries for all time intervals. We also have a minimal amount of total customer demand that needs to be satisfied over all time intervals. And finally, we are given a time required for recharging a battery. A solution to our problem is given by three variables. The X variables indicate whether a station is built at the location or not. The Y variables tell us how many battery slots are required at each location. And the A variables give us the allocation of customers between the locations during the time intervals. And the objective function of our problem is to minimize the total building costs of the system. Now I want to present to you our first heuristic, which I've called the relaxed MILP heuristic. This heuristic can either be used as a standalone version or can also be used in the large neighborhood search, which we will represent later to repair a solution. And the idea of this heuristic is that we relax our Y variables and allow them to be continuous, and the remaining problem remains unchanged. Then we use a MILP solver to solve this relaxed problem, and we then derive a feasible solution by simply rounding up all non-integer Y values. So now I will give you an overview of the large neighborhood search that we have developed for this problem. A large neighborhood search is an iterative process that iteratively destroys and repairs a given solution. So for our large neighborhood search, we've first given the set of locations which contain open stations in our solution. And we first generate a location set lambda in an iterative way. So we select a random vertex from our graph and add it to our set, and we also add our random neighbors of this vertex to our set, and this process is repeated k times. From this location set, we then derive our set of locations that we want to destroy and the set of locations that we consider when repairing the solution. We simply destroy all locations that are opened in our solution, which are also contained in the location set lambda. And then when we repair the solution, we consider all the locations in our location set lambda, and the solution is repaired by applying the relaxed MILP heuristic described in the previous slide. We have two groups of instances. First, we have a group of completely artificial testing scenarios, and then we have one larger instance that is based on taxi and bus data of Manhattan. So first we take a look at the artificial instances. We have in total tested three different algorithms. First we have solved our problem as a pure MILP approach and used Gorobi to solve the problem. Then we have also applied the relaxed mill heuristic as standalone variant to solve the instances. And finally, we have also applied our large neighborhood search to solve the instances. Here in these figures, we show box plots of the optimality gaps of the instances grouped by the number of locations and number of trips. So each instance was evaluated on two different values for the mean, which is the minimal demand that needs to be satisfied. So in general, we can observe that the pure MILP approach works relatively well for smaller instances, but becomes worse and worse the larger the instances become. And the larger the instances become, the better our other two approaches are compared to the MILP approach. So in the first figure, we can see that for the largest instances, our LNS is able to outperform the other two approaches and generate the best results. In the second figure, however, where the mean is set to 80% of the total demand, we can see that the relaxed mill heuristic becomes a lot better and performs about equally well as the LNS. And for the largest instances, it is slightly better than our LNS. Now let's take a look at the results for our real-world inspired instance. This instance has been evaluated on 5 different values for the mean. So here we can see that within our time limit of 30 minutes, the MILP approach is only able to find solutions for 2 values of the mean, and the relaxed mill heuristic is able to find solutions for only 3 values of the mean. On the other hand, our large neighborhood search is able to find solutions to this instance for each value of the mean, and also for the low values of the mean, the LNS usually outperforms the results of the other 2 approaches. However, we also want to mention here that the performed number of destroy and repair iterations in our LNS is not as high as we want it to be, and this is still future work to further improve the scalability and performance of our LNS, which at the moment is still a very basic LNS that has still a lot of room for improvement. With this, I conclude my presentation. Thank you very much for your attention.
Okay, thanks for the presentation. This was a short one, and the time for question and answer starts now. And you can find the link to the rooms for both session 16 about routing TSP and session 17 about routing mobility in the chat. Just look for a message by Florian Mishek. Thanks to everybody, and have a great continuation of the conference.